If you keep guessing how many epochs to run, you either overtrain or leave accuracy on the table. We will read learning curves in Python and add early stopping, so you automatically stop when the model peaks. You feel the pain when training drifts from improving to degrading, and you do not know where to stop. By the end of this video, you will read training and validation curves, pick a sensible stopping rule, and hook up a simple checkpoint, so training halts at the best moment. That saves time and gives more reliable models. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Early stopping solves a common workflow problem. You train iteratively across epochs and watch a validation loss. At first, the validation loss drops, then it flattens, then it climbs. Picking the final epoch by eye is noisy and wasteful. Early stopping makes that decision automatic. It recognizes the peak and restores the best model. That reduces overfitting and shortens runs when you tune models on modest hardware. Intuitively, learning curves are a story. The training curve tells how well the model fits the data. The validation curve tells how well it generalizes. When the curves diverge, the model is memorizing noise. Early stopping listens to the validation curve and says stop when generalization starts to fade. We will build a tiny synthetic experiment. The dataset will be linear with added noise, so we can clearly see underfit, fit, and overfit phases on the curves. Then we will split into train and validation, run gradient descent while recording losses, and finally, implement a patience rule to save the best weights. That makes the concepts concrete and repeatable. This snippet creates noisy linear data and measures a zero model baseline loss. This example builds a simple input and output where the signal is linear, but noise is added so we can tolerate some error. The key idea is to have a baseline to compare against, so learning actually makes sense. The snippet prints a baseline loss for a model that always predicts zero to provide context for the training loss you will later see. That baseline helps you judge whether learning is happening at all. When the baseline loss is high compared to trained loss, you know the model learned signal rather than noise. Now we will split the data and set up a validation view. This snippet makes a train validation split and evaluates validation loss. This code divides the synthetic samples into two sets so we can measure generalization independently from fitting. The top lines create a validation set and then compute loss for the untrained or baseline model on that set. The important point is to keep the validation data untouched during gradient updates. The snippet also shows how to compute mean loss per sample and records that value so it appears on the learning curve. If you change the split ratio, you will change how noisy the validation curve looks. Smaller validation sets make the curve jumpier. Next, we train with a simple optimizer and log losses each epoch. This snippet trains with gradient descent and records the best validation epoch. This example runs an iterative loop that updates weights to reduce training loss while computing validation loss after each epoch. The first lines initialize weights and the gradient step. The loop then computes predictions, training loss, gradients, and applies the weight update. After that, it computes validation loss and compares it to the best seen so far. The snippet also records both training and validation losses into lists for plotting. If you use a larger learning rate, updates are faster, but the curve may bounce. A smaller learning rate smooths the path but needs more epochs. The code highlights the trade-off without getting lost in math. Next, we add an early stopping rule and a checkpoint save. This snippet applies patience-based early stopping and saves the best weights. This block watches the validation loss and keeps a counter for how many epochs passed since the last improvement. When a new best validation loss appears, the code saves the current weights as the checkpoint and resets the counter. When the counter exceeds the patient's threshold, it halts training early to avoid further overfitting. The key lines are the comparison that detects improvement and the logic that writes or stores the best weights. If you increase patience, the training tolerates temporary noise and may find a later, better minimum. If you shrink patience, training stops sooner and you save compute. Finally, we restore the saved model and report final validation metrics. This snippet restores the best checkpoint and reports validation performance. This final step loads the saved weights that correspond to the best validation loss and evaluates the model back on the validation set to confirm performance. The snippet then prints or returns the restored validation loss so you can compare it to the tracked losses. The important idea is that the checkpoint is the canonical trained model, not the weights at the last epoch. Restoring ensures you deploy or evaluate the version that actually generalized best. This checkpoint restore is the difference between stopping early and deploying a degraded final snapshot. In a real project, you would map this small loop into your training loop, swap the synthetic data for a real dataset, and save checkpoints to disk. The same early stopping logic works for classification or regression, and it scales to larger models by monitoring any validation metric. Recap: early stopping watches validation performance and stops when generalization decays. Use it anytime you train iteratively and want to avoid overfitting or wasteful epochs. One caveat: noisy validation signals can trigger premature stops, so patience or smoothing helps. Next step: try tuning the patience parameter and monitor how validation peak timing shifts as you change it. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.